So I hope you're ready for part 2, talking about the certificate of immunity, this magical piece of paper that will make it all okay, right? So in part 1, we talked about the idea of how the immune system works, the innate immune system, which is non-specific and acts quickly, and the adaptive one, which includes making antibodies and remembering that you've met this bacteria or virus before. We've also talked about how vaccines sort of can be tested, testing antibody levels, presuming you know what antibody to test. And so now we go to actually talking about vaccination. So let's first talk about the idea of protection, how protective a vaccine is. You know, they talk about how good a vaccine is. And so we actually have to know that there's actually different definitions of protection. So there's two ways you could define protection. One is an all or none method. And that means if you say you're protected 80%, it means 80% of the people are completely protected and the rest, 20%, they're not protected at all. The way you explain this is there's a threshold effect. So for example, let's say you need to pay a certain amount of money to get into the fair or Disneyland, $100. Well, luckily there's a man who's handing out money, $100 bills. But, he's not handing out to everybody. Only to most of the people. That's like 8 out of 10 people. So if you get the money, you're in. If you don't get it, you're out. There's no in between. And that's the idea of a threshold effect. You need a certain amount to cross that threshold. And if you don't make it, you just don't make the cutoff. And then there's the partial definition. Everybody's protected 80%. So nobody's really protected 100%. Nobody's really protected 0%, but everybody's protected somewhat. As in, compared to somebody who didn't get a vaccine, you're 80% less likely to get it. The way it correlates to real life is that we say everybody has a very good response initially, but their levels decrease over time, and you just sort of get less protected because everybody is vaccinated at a different point in time, right? So if you take a sum over time, people vaccinated here, there, right? It all averages out to be, say, 80%. And so in terms of pertussis, Tdap, tetanus, diphtheria, acellular pertussis, we all know that it decreases over time, the effectiveness. And so one study in Canada said it was pretty good within the first 3 years, 95% or above. And then it decreases pretty rapidly, 4 to 7 years, 63, and after 8 years, 22%, not doing very much. And how do I know this? Well, I happen to get pertussis myself. I know it's not a great vaccine. And when I was talking to an infectious disease doctor, he was saying, yeah, 5 years might be a bit long. And wow, what do you know? Per the study in Canada, it seems like 5 years is quite a bit longer. So here's the thing though, with pertussis, it's not usually a big deal. As in, if you're young or old, it's a big deal. But if you're not young or old, it just makes you feel like you're coughing your lungs out and you might as well die. That's about it. And you'll cough for a long time after you're, quote, better anyways. So there's also the hepatitis B vaccine, which, I have seen evidence that it wanes over time. The second thing is, how do we make a vaccine? There's all these stock market companies that we know are making vaccines. That's why all of a sudden we're like, how did this company show? Oh, they're making a vaccine. Oh, they have vaccine in their name. Like Novavax. Well, I think they make vaccines. Well, they do. Realistically, it's not going to be till many months that a vaccine comes out. But let's talk about sort of how we make a vaccine. So the goal is your body has not met this virus before called coronavirus. And we actually don't want it to be unprepared when it meets it. So again, we said we can't do much with your innate immune system, but if you could learn to make antibodies to this, you'll have some preparation, right? Okay, so how do we get your body to do that? Live attenuated is the simplest and I would say probably the earliest. Just take the pathogen, bacteria, virus, whatever, and weaken it, and just give it to people. So Jenner and Pasteur were famous doing that, right? With cowpox. It's very natural. It's still there in your body. It still does stuff, right? It's weakened, but it's still alive. So your body will react to it, make antibodies in the way it naturally does. Antibodies to this part, to that part, all the parts. Your body will work together, all together, to fight this. And then when you meet it again, you're ready for it. But there's a slight risk to this. Most obvious with the oral polio vaccine. So you may actually get polio, unfortunately. That's a very low risk though, 1 in a million. And the thing is, some places the oral polio vaccine is still used because it's cheap, it's cost effective. You know, other vaccines, the ones that say you have to inject, I think you need something called a refrigerator. And when you're in the middle of nowhere, I shouldn't say middle of nowhere, in many places you don't have a refrigerator. MMR is another example, measles, mumps, rubella, live attenuated. That's why certain people can't get it. Then there's inactivated. So they're not quite alive anymore. They can't hurt you. But also your body is not going to react to it as much. If you just think about it logically, your body's like, hey, it's dead. What do you want me to do about this? It's dead, right? So sometimes you need something like an adjuvant, something to stir up the body's immune system, to get it working, to get it excited. And so things in this category would be the influenza vaccine, whole cell pertussis, not the acellular pertussis, hepatitis A. There's also a purified subunit. You just try to take that antigen and you purify to make it just react to that. So you take these toxins, you purify, and you say, okay, these are the bad parts of bacteria. I want you body to learn how to fight against this. The problem is some of these don't last very long because your body is not getting all the parts of the immune system together like it would otherwise. Because sometimes you don't really recruit certain T cells when it's not alive. And so, for example, the acellular pertussis, the part of Tdap, it's this, and so it didn't last very long. It works, but yes, the staying power, not great. So they developed something called conjugation. You conjugate it, give it another part that the body reacts more to. And then the sort of the pneumovax, the one against Streptococcus pneumoniae, that's one of these ones. And then you have the fancier, sort of designer ones. So, you know, in the lab, we're sort of having this conflict. You know, some people say, we got to just design stuff ourselves. Other people say, let's just go with real life. And so it's difficult, right? You know, because we think we could design awfully well, but, you know, sort of, we can't. So we have to test it when we design it because, you know, in our simulations it works well, but in real life not quite so well. So they came up with a recombinant protein. So they sort of make the protein, the designer protein. They're like, oh, we think you should react to this. So let me make this for you to react against. So actually some of it worked quite well, like the HPV vaccine, the human papillomavirus. You actually have a better response, a higher antibody response than if you actually got the infection itself. So let's sort of take a side branch and talk about a neutralizing antibody. So sometimes people talk about a neutralizing antibody. They test their neutralizing antibody. First of all, just like we said this term absolute, there is no such thing as absolute. But the idea is, if it's neutralizing, it sort of takes out the virus. So even if your immune system's not working, it's okay, this virus has been taken out. Take your time, no hurry. He's not been wounded. He's been actually taken out. He can't cause you any more harm. One practical way is he can't actually bind and go into your cell. So you can only stay outside. Can't cause much harm that way, right? We don't need it to be neutralizing for it to be effective though. So it can just sort of hang on to the thing. Sort of like how, if you remember back in the days when we played football. I mean, in the NFL it's sort of the same. But you know, one guy sort of hanging on to this rusher who is just continuing to take off with this guy. The guy's not stopping him. But he slows him down enough that other people could catch up and then together they could take him down. Because the body has lots of immune cells. So you're just like, hey, this guy, I can't do anything, but it's like a civilian arrest, but I'm just sort of putting up a flag that you should come in and help me. And then the other cells will come in and help you, the bigger, stronger cells, let's say. But this is important when you're designing something, right? Because you might as well design something that's neutralizing. Why not design the best? Well, again, it's not quite so simple. So in the antibiotics world, dealing with bacteria, we talk about bactericidal and bacteriostatic, meaning some antibiotics kill the bacteria, some just sort of delay and slow down its growth so your body's immune system can take care of them. Obviously, you want bactericidal, right? Well, no, it's not quite so simple. First of all, sometimes they're bactericidal, sometimes they're bacteriostatic. Second of all, sometimes actually bacteriostatic antibiotics are better. So, for example, HIV. There are neutralizing antibodies, but guess what their issue is? They're too specific for a certain strain of HIV, and it mutates a little bit, and it doesn't recognize it anymore. Well, what good is that? And there's also some data that non-neutralizing antibodies to HIV can be protective, and if you don't have those, you won't get the infection. Well, I would prefer to have that, wouldn't you? So, in terms of current vaccine development, we talked about sort of the traditional ways, and there's new companies. Moderna is probably one you've heard of. They're making something called an mRNA vaccine. mRNA standing for messenger RNA. So the way our body's cell work is that we have a lot of different sort of factories or units inside. We have the nucleus where your DNA is stored. We have the sort of the outer sort of, the cell wall where outside is everything outside and inside is our own little world, right? And then it's quite a bit complicated going in and out, right? There's a lot of barriers, shall we say. That's why I call it a semi-permeable membrane, because some things come in, some things cannot come in so easily. And the way it works is that we have DNA, that's our genetic code, right? Coronavirus is RNA, right? But ours is DNA, RNA. They're sort of all the same. They're sort of complementary. You can mix and match. But our DNA gets translated into something called mRNA, messenger RNA, and that goes to a factory, a protein-making factory called the endoplasmic reticulum. And then from there, they sort of take that code, which has been translated for them, and they make it into actual physical protein, antigen, whatever you want to call it, right? And so the way these mRNA vaccines work is they're actually harnessing your own body's cells to make the antigen that you're supposed to react against. Doesn't that seem brilliant? So instead of them having to actually make these proteins, which may be a bit complicated, right? Instead of them actually having to figure out a way to make mice or whatever, chicken eggs, make a lot of these proteins, they just tell, hey, your body, make it for me. So the difficulty they've encountered, which I think they've sort of done a good job overcoming, is, well, how does this mRNA get into the cell in the first place? Because the cell doesn't want it. It doesn't want strange mRNA. So they've had methods and varying successes, but they're pretty good about getting that mRNA into the cell now. And so they've come up with a way of making a protein, and your body's going to make that protein, and your body's going to react against the protein it just made, because it's actually a bacteria's protein. How brilliant, right? I mean, it is a way, it seems it's much faster, right? It's much easier, right? You just make a little bit of stuff and your body will do the rest. And so that's one of the current sort of methods of developing vaccine, but even Moderna says, earliest with expedited emergency treatments, not going to be till fall of this year, which is many months away. Unless you're in California, which there is no fall, right? Then it's who knows when it's going to come. So I think that's a little bit about this whole idea of vaccines, how they make it. We've talked about how you sort of test for antibodies, levels, saying, hey, whether you're immune or not. And so we've sort of covered what it takes to get a certificate of immunity. And I think we mostly think that, it's going to be vaccine versus certificate of immunity. But I think that you can't really come up with a practical certificate of immunity, and so it's just going to be vaccinating people. And when we vaccinate people, there's a lot of articles about this. We just sort of say, hey, we get the vaccines out. We're not going to bother testing people, right? That's something we already did when you approved a vaccine, how effective it is. And we just know how many people we have to vaccinate to make it effective for the whole population to develop herd immunity. And that concludes part 2.